Welcome all. So today we will continue our lecture on the issue of blast loading and its effects on the structure. So today we will see the effect of loading and on the structures. So continuing from the last time, let me give you a quick recap. In the last time what we learnt was, let us say a blast loading is occurring, okay, at a certain point, okay. So we looked how to calculate the effect of the blast loading at a certain given point, okay. In order to do that, the first thing is to classify the type of explosive, okay. So we have to convert it into equivalent amount of TNT, okay. Once we have converted into equivalent amount of TNT, we need to increase it by 20% to account for the uncertainty. If it is pure TNT, the explosive is pure TNT, then this increase is not required, and if it is any other material than TNT, then we might increase by 20% to account for the uncertainty. After that, we need to categorize the type of the blast depending upon what is the location of the blast relative to the surface, the location in the air. We can classify as free air burst or surface blast, okay. So after we have categorized these quantities, what we need to do is that we need to calculate the distance between the point of interest to the point where blast load is occurring, okay. So we need to calculate the standoff distance, okay. Once we have calculated the standoff distance, we calculate the Z factor, okay. So Z factor is calculated by standoff distance against the divided by cubic root of the weight, okay. Once we have the Z quantity, then we can take the respective curves from UFC 3340 or TM5 1300, okay. And from that curves, okay, on the x axis Z is there, and on the y axis we will have peak incident pressure, peak reflective pressure, impulse, positive impulse duration, negative impulse duration, time of positive phase, time of negative phase, positive blast wavelength, negative blast wavelength. So all these quantities will be there. So we will read on the x axis the Z point, and we will calculate where it cuts the y axis, okay. So we can calculate all these given quantities, okay. All these quantities are scaled with respect to the weight, okay. So once we have that scaled value, then we will multiply those value with cubic root of weight, and we will get the base quantities in their respective units, okay. So this way we can calculate the effect of the blast at any given point, okay. So we did some examples and we learned this procedure, okay. So after having this armor, we will go ahead and we will try to calculate the effect of the blast loading, the pressure, incident pressure, reflected pressure, impulse on the structure, okay. We will apply the loading on the structure and see how the structure behaves under this blast loading, okay. So the effect of the blast loading depends upon certain factors, okay. What it will do to the structure depends upon the factors, okay. So it depends upon the magnitude of the explosion, meaning it depends upon the weight of the explosive. It depends upon the location of the explosive relative to the structure in question, okay. So this has some parts. One is if the structure is confined or unconfined, okay. So if the blast is occurring in a confined structure or if the blast is occurring in an unconfined structure. So we have seen that we categorize our blasting in two phases, confined and unconfined, okay. So the location of the explosion relative to the structure in question, okay, unconfined and confined. And if we again go deep dive into this confined and unconfined issue, we will see that in an unconfined blast, the distance between the blast and the location of the structure, okay, that is the standoff distance plus the location of the blast relative to the structure, okay, whether it is a free air blast, whether it is a air blast, whether it is a surface blast, okay. So that will again be a function of the relative location of this two, okay. So depending upon these factors, okay, the amplification in the pressure wave will occur. Same is true for the confined blast. In confined blast also, depending upon the confinement, it will be either fully ventilated, partially ventilated or fully confined. Okay. So, depending upon this factor, the attenuation, the amplification of the pressure will occur. Okay. So, in both the cases, the relative location between the blast loading and the structure plays an important part. Okay. The geometric configuration of the structure. Okay. So, as we have seen also last time, the geometric configuration of the structure, okay, whether it is a 3-part structure, fully confined structure. Okay. So, all this configuration will determine how the blast load is spread out with respect to the structure. The structural orientation with respect to the explosion and ground surface. Okay. So, the orientation of the structure with respect to the blast loading, okay, whether the structure is like this. Okay. So, the blasting is occurring like this or the blasting is here. Okay. So, the relative orientation, these two blast loading will have different effects on the structure, and the location of the blast loading with respect to the ground surface will also play a crucial role. Okay. So, all these factors, the boundary conditions, the relative distance between the explosion and the structure, the configuration of the structure, okay, the magnitude of the locations, all these things plays a crucial part in determining what will be the final effect of pressure and the associated gases on the structure. Okay. The procedures presented here for the determination of external blast load and structures are restricted to rectangular structure positions above the ground surface, where the structure will be subjected to a planar shock front. Okay. It means that whatever things we are discussing, we are discussing structures which are above ground. Okay. We are not discussing right now the underground structures. Okay. And the structure will be subjected to planar shock front. It means that if the blast loading is occurring like this, what the structure sees at the end of the day is a planar front. Okay. The blast normally occurs in this fashion, but when it hits the structure, we are assuming that it forms a planar wave front. Okay. So, this is our assumption. The structure is above ground and the effect of the blast that the structure is seeing is a planar wave shock front. Okay. These processes can be extended to include structures, other shapes. Okay. We can include other shapes like spherical shapes structures, okay, cylindrical shape structures, as well as structure position at below the ground surface. Okay. So, we are starting with the basic things. Okay. We are starting with the rectangular type of structure. Okay. We are assuming that my structure is located above ground, it is a rectangular structure, okay, and the effect of the blast, okay, is in the form of a planar wave front. Okay. Okay. So, we will now go into the details. So, introduction to forces on structures from blast wave. We will now see how the forces due to the blast waves, how the forces are transmitted to the structure. So, forces on structure due to blast loading, it depends upon peak pressure. Okay. So, earlier we seen that the effect of the blast loading will depend upon the weight of the blast, the distance between the structure and the blast, the orientation of the structure, okay, the geometry of the structure, the configuration of the structure, the material of the structure, and after that we have seen that we are assuming that the structure is rectangular, okay, it is seeing a planar wave front, okay, and the structure is located above ground. Okay. So, considering all these things, okay, the forces which the structure sees will depend upon the peak pressure of the incident and reflected shock waves. Okay. So, the forces that the structure will see will depend upon the incident and reflected shock waves, the pressure quantity of these things. Okay. It will also depend upon the impulse. Okay. It will also depend upon the total area under the pressure time curve. Okay. It will also depend upon the dynamic pressure caused by the particle or wind velocities behind the shock front. Okay. Behind the shock front, whatever is the wind velocities. Okay. So, if they are exerting any dynamic pressures, the forces will be also a resultant of that. Okay. So, we will now try to understand these forces so that they can be used in the structural design to resist the blast effects. So, key parameter of blast loading. Okay. So, key parameter includes the peak incident pressure. Okay. So, here we can see a graph of peak incident pressure. Okay. So, this is a graph of peak incident pressure versus peak dynamic pressure. Okay. Okay. So, here peak dynamic pressure, particle velocity and density of air behind shock front, they are evaluated. Okay. So, peak dynamic pressure, that is resulting from the wind generated by the particle velocity behind the shock front. Okay. What this graph is basically doing is that depending upon the peak incident pressure, we are able to calculate the peak dynamic pressure, peak velocity and density of air behind the shock fronts. Okay. So, all these quantities we can calculate using the peak incident pressure. Okay. So, particle velocity, that is the velocity of the air molecules moving behind the shock front. Okay. So, these parameters are interrelated and depend solely on the peak incident pressure. Okay. So, basically peak incident pressure is the guiding quantities and all these other quantities can be derived from that. Okay. So, peak incident pressure is the basic signature of a blast loading. Okay. So, pressure time history of the blast loading, we have already seen the pressure time history of the blast loading. So, we will reiterate it. So, it is having a, this is the pressure time profile. In reality, there is a rise, okay, there is a steep rise and this rise in nanoseconds. So, normally this is neglected and this is taken as a straight curve, okay, and it rises above the ambient pressure, it rises suddenly in nanoseconds, then it falls back, goes into the negative region and again subsidizes to the ambient pressure. Okay. So, this is called the positive phase duration. So, this is the positive phase duration and this is the positive pressure, negative pressure and this is the negative phase. Okay. So, the signature consists of an instantaneous rise to peak pressure, there is an instantaneous rise, a positive phase where pressure decays back to ambient. So, there is decay and it goes back to the ambient and after that ambient the suction or the negative phase occurs and it after that it subsidizes to the ambient things. Okay. So, both the incident and reflected pressure follows this pattern. Okay. So, both the incident, so this can be a signature of the incident pressure and this can be signature of the reflected pressure. Okay. Both will follow the same nature. Okay. And this curve is called as Friedlander's profile. Okay. So, in blast terms the pressure profile, okay, this pressure signature is known as the Friedlander's profile. Okay. So, what happens here is that each pressure curve has a decaying type of signature. Okay. So, the red dot denotes the decaying type of signature. Okay. So, in order to design it, what we do is that we idealize it using a triangular phase. Okay. So, a triangular nature is assumed to idealize this behavior. Okay. So, for design simplification, the actual decaying pressure time curve is replaced by an equivalent triangular pulse. Okay. So, this pressure time curve is replaced, this has a decaying nature like this. So, this is replaced by an equivalent triangular phase. Okay. So, there are two things. Okay. One is the actual positive phase duration, that is denoted by T naught. Okay. And there is a fictitious positive phase duration. Okay. This is TOF. Okay. And what we say is that the area under both the curves are same. Okay. So, the area under this curve is denoted by I. Okay. So, we are saying that the total impulse is same and if we are keeping the magnitude same. Okay. So, this is from the actual nature. Okay. So, the actual nature, the total impulse is this much. Okay. Let us say this is I positive. So, this is the total nature. Okay. If we replace it by a fictitious triangular curve, okay, so the area under this curve is half of P. Okay. So, this P we are keeping as same. Okay. And using this relation we can derive the fictitious positive phase duration. Okay. So, we have taken the same effect and we have replaced this thing with a triangular phase. Okay. So, where I is the total positive pulse and P is the peak pressure. Okay. So, this is how we are deriving the quantity. Okay. We are deriving the positive quantity. Okay. This green curve, okay, this dot. Okay. This approximation applies to both incident and reflected pressure. So, the same thing we can use for the incident as well as the reflected pressure. The equivalent duration for dynamic pressure is assumed equal to that of the incident pressure. Okay. So, the same thing can be done for the reflected pressure also. So, here this is PSO, it can be also R, and correspondingly I will be ISO or IR. Okay. So, this is how the actual curve is translated into a triangular curve which will be used for the design purpose. Okay. Same treatment is done for the negative phase. Okay. So, there is a rise time approximately 1/4 of the positive phase duration. Okay. So, this is we assume as 1/4, approximately 1/4 of positive phase duration. So, we calculate a negative phase duration, where I negative and P negative are the total impulses and peak pressure of the negative pulse. So, similarly same treatment we are doing this for the negative phase also. So, the negative dynamic pressure generally has a minor effect on the structure and can be often neglected in the design. So, the same treatment is done to derive the equivalent triangular curve. So, from here to here we take as 1/4, and from here we calculate the T of total. So, there is a time gap between positive and negative phases. What will happen is that here the curve is continuous, but if we look closely, here there will be a time gap between the positive and the negative curve, if we try to approximate it. So, the fictitious positive phase duration is shorter than the actual. This is shorter than the actual one. So, this creates a time gap between the positive and negative phases. So, the actual structural analysis should preserve this gap or represent load phasing accurately. So, we have to account for the change in the nature of the loading. So, there are 4 general components of the forces imparted by the blast loading. There is the incident pressure force. So, this is the direct force from the initial blast pressure wave hitting the structure. So, this is the first thing that the structure sees. So, if the structure is like this and there is no reflection, let us assume that there is no reflection, then what the structure sees at the very onset is the incident pressure. So, the force caused by the incident pressure, this is the first thing that the structure sees. Dynamic pressure force, this is the force due to change in pressure as the blast wave moves. Reflection forces, these are the force caused by blast pressure reflecting off nearby surface that interfere. So, due to the nearby surface such as the ground and all, if there is a reflection, then the structure will see the reflected pressure also, and due to this reflected pressures there will be reflected forces. There will be negative pressure force. So, these are the forces from the negative pressure following the shock wave. So, what happens is that we have seen that each blast event will be accompanied by a negative force. We have seen that the blast wave has a positive phase duration and it has a negative phase duration. So, what will happen is that once the positive phase ends, there is a negative phase will begin. So, what it will do is that it will create a suction in the structure. So, let us say if the positive phase is hitting the structure like this, and the structure is trying to bend like this. So, after that the suction occurs. So, the structure will try to bend in this fashion. So, in design we have to take into account this thing. So, we have to take into account both positive and negative phase duration. So, these are some of the guidelines that we need to follow. We need to account for the incident forces, we need to account for the dynamic forces, we need to account for the increase in forces due to the reflection, and we also need to account for the reversal in the direction of the forces due to the negative forces. So, key considerations. So, again we have already seen we have to account for the geometry of the structure and size. We will have to account for the geometry, rectangular, triangular, similar, the size of the structure with respect to the location of the blasting. Okay, this will determine whether we are having a planar front, okay, or the pressure is changing as the length of the structure increases. Orientation to the direction of the shock front. Okay, so if the blast is occurring at the top, okay, so it will create the spherical fronts. Okay, so this will be considered as the free air blast. If the blast is occurring at the front, okay, so it will act as a air blast. If the blast is occurring in the surface, okay, so this will be considered as the surface blast. Okay, and design purpose concerning blast loading. Okay, so this comes under the performance based design. Okay, so whenever a structure is designed, okay, its performance normally is fixed. Okay, so in our conventional design, we design normally in the RCC design, we are used to design for the crushing of concrete. Okay, in the LRFD designs, we have different limit states. So in different limit states, if you look into the strength limit state, we are used to design for the crushing of the concrete or breaking of the bars. Okay, this is one of the limit states depending upon the strength. For the deflections, okay, we normally like our structure to behave in a elastic fashion. Okay, so normally we are used to have only one performance level. Okay, but in the blast loading case, okay, there can be different performance level, and depending upon the uses of the structure, okay, a performance level specific to this structure can be fixed. Okay, this structure can be designed so that the cracking does not occur. Okay, let us say for example in a nuclear containment structure, okay, we will design for a performance level where cracking does not occur. Okay, if this is a bunker type of structure, okay, then we will design it so that there is no splintering, no fragmentation. Okay, so different type of design performance limit states depending upon the uses of the structure can be fixed out here. Okay, so we have to take into consideration all these points. Okay, so since blast is a very complex phenomena, okay, we normally make some assumptions. Okay, so now we will look into those assumptions. Okay, so first assumption, big assumption that we are making is that the conventionally all of our structures are generally of a rectangular nature. Okay, so the treatment that we are doing right now is considering the structure as a rectangular structure. The magnitude of the incident pressure normally it is considered as 200 psi. Okay, it can be more than that, but we are on an average designing in the range of 200 psi. The structure is within the max stem range. Okay, the high pressure region where shock waves merge. Okay, so it means that if my blast is occurring like this, okay, the structure is seeing a planar front. Okay, and this blast wave, okay, this mixture of the incident and the reflected pressure, they are forming a max stem, and the structure is seeing a planar force, and this max stem is bigger than the structure. The max stem extends above the building height. So basically our structure is seeing a planar type of force. Okay, so these are some of the assumptions that we are making. Okay, whenever we are trying to go beyond this assumptions, okay, we will have to tweak the analysis. Okay, let us say our structure is above the max stem. Okay, then the pressure distribution above the max stem will not be planar. Okay, so it will change, okay, with the distance. Okay, so we will have to account for this changing variation. Okay, structure is non-rectangular. Okay, then there will be interaction between the curved surface and the blast pressure. Okay, so we will have to account for that. Incident pressure is more than 200 psi. Okay, then also we will have to make some considerations. Okay, so as we are dealing with different types, different geometries of the structure, we will have to refine our analysis as we go further. So now we are looking into a case, okay, where our structure is a rectangular structure, it is an above ground structure, and it has no openings. Okay, so we will now see what are the loads on the front wall. Okay, so pressure variation on the front wall. Okay, that is we are considering normal reflections. Okay, so when the shock front strikes the front wall parallel to the shock front, okay, pressure instantly rises from 0 to the normal reflected pressure. Okay, so this is my front wall, and the structure is hitting the front wall. Okay. So, the rise in pressure is instantly from the ambient pressure to the reflected pressure. Okay. The clearing time Tc, we are defining a term Tc. Okay. So, this is related to the loading of the blast reflected pressure. So, S is the clearing distance, that is the minimum of the structure height or half of the width. Okay. R is again a different factor, and Cr is the sound wave velocity affecting the region. Okay. So, this is the clearing time. Okay. So, after this clearing time, pressure on the front wall equals to the sum of the incident pressure and the drag coefficient. Okay. Once the clearing time is done, okay, once the reflected pressure has applied, after that the incident pressure and the drag pressure comes into picture. Okay. And CD equals to 1 CD. So, 1 is considered for this pressure range. Okay. So, the drag coefficient is considered as 1. Okay. So, this is the loading of an above ground structure. Okay. The structure is rectangular in nature, it is having no openings, and the shock the shock front strikes the front wall parallel to the shock front. Okay. Okay. So, the pressure time curve verification and the impulse calculation. Okay. So, we will see how the pressure time curves occur. Okay. So, this is the how the shock hits the wall. Okay. This is in plan and this is in elevation. Okay. So, this is how the structure is hitting the blast is hitting the structure. Okay. So, instantly we will see the reflected pressure, and the reflected pressure will be applied till the time Tc, the clearing time Tc, as we have seen here. Okay, this is the clearing time Tc. Okay. So, after the clearing time Tc, the reflected pressure is revealed. Okay. The reflected pressure is removed. Okay. After that time Tc, okay, there will be incident pressure and the drag pressure. Okay. So, for short pressure pulses, pressure time curves must be verified for accuracy. Okay. So, this is the equivalent design curve, okay, that we will use, okay, for the blast loading. Okay. So, we have to construct a second curve, okay, where the intensity due to the reflected pressure is used. Okay. So, this is same thing, okay, PR half equals to the intensity. Okay. So, this is the same principle that we have used. Okay. So, it means that though the reflected pressure, okay, it is relieved after a time Tc, okay, the total intensity of this reflected blast curve, okay, this reflected blast curve should match with the actual intensity. Okay. So, then we make this curve. Okay. So, this is used to calculate the loading on the wall. Okay. So, this is due to the normal reflections. Okay. So, this is how we will construct the curve, so that this loading is applied on the front walls. Okay. So, I will stop here. Next time we will continue with the same treatment. Thank you.